Everyone, at least if you are in Europe. So my name is Christian Rinderknecht, and I would like to thank Michel Moni for inviting me here. Also Adrian to have done the heavy lifting and talk about the protocol and introducing, in general terms, smart contracts. So can you hear me? Can you see my slides? Is it okay? All right. So I do have slides because I'm left-handed. No, I'm joking. I'm not. So this is not the first time I give this talk. I made some changes. I do, though, recognize some familiar faces, and it feels like I'm back teaching undergraduate students in college. It's kind of weird. So some of you are going to get bored, for sure. I think I used to have a longer personal introduction. I think nowadays I will just go by, I used to be one of Michel Moni's PhD students. And I passed, so I guess this is enough introduction. Thanks, Michel, for being so famous. Makes my talk so short now. So yes, so LIGO, tomato. Pick the one you like. It's at first it was the name of a project. It is one or many languages. I'm going to explain that for writing smart contracts on Tezos, other than writing Mikkelsen. So it's a high-level language. It's also a company that is now called LIGO. You will see that there is a website as well. So what we have done basically is develop that language we call it LIGO, and also some tooling around it, because nowadays a naked language is of no use. So the other component you need to get a language adopted is tooling. Of course, you need also libraries and community. So we are working on that. But we started obviously with the language and the compiler and the tooling, because this was the minimum we had to do to be taken seriously. So there is a website. You can see the URL down there, and so you're welcome to have a look when I'm speaking. Yes, we do of course training for people interested in writing their first dApps, of taking their first steps in writing dApps on Tezos. I'm sorry, I can't look at all of you in the audience because the location I'm with, so I'm not ignoring you on the right side. It's camera work. You have to keep your marks. Yes. So what do we mean by high-level language? We mean a language where you have variables, you have expressions, you can define your own data types, and you can actually destructure your data easily. This can be done, of course, in Mikkelsen, but it's more complicated. I mean, you can do anything on Mikkelsen, but it's very complicated because you have no variables, for example. So you have to keep in mind the order in which you put things in the stack and what it is you put in the stack. Okay, so it's much nicer to have names to talk about things. So this is very much like a normal mainstream programming language, okay? Then, of course, this is currently this is not a general programming language. So this is a domain-specific language for writing smart contracts. And this may seem obvious, but this creates some tension sometimes. For example, we have in the audience and later on speakers from Madfish Solutions that are trying to target LIGO for compiling from Solidity. And this creates some tensions because some features you would expect in a mainstream language are not present there because it's still a DSL. So even though it looks like a general programming language, it doesn't have all the, the bells and whistles you would expect from a normal mainstream language. It is open source. And you're welcome to always to leave us some GitLab issues. Sometimes we are asked in the team to compare LIGO with other programming languages you heard about before, about SmartPy, Solidity, others, Juvix. Unfortunately, we don't know. We don't have time yet to look at them. I even found a dead Jira issue to compare us with SmartPy. So the situation is very dire. We haven't done the homework yet. We will do it when the time comes, I suppose. Well, we don't see others as competitors. Perhaps this is the good news of this. Why did I say earlier that LIGO is perhaps many languages? Because in fact, it looks like many languages. And from the inception, we didn't want bike shedding, useless discussions on syntax to clutter the community, the future community of LIGO. So we decided to offer different concrete syntaxes. So they do look like different languages, but they are not. Internally, the compiler is the same for the three syntaxes. And we went beyond just syntax. We wanted to offer different programming paradigm. So one of them is Pascal LIGO, which basically offers you lots of keywords and the possibility to do a limited kind of mutation assignments, if you will. The second one is Camel LIGO, which is inspired by OCaml. So actually, it's a strict subset of OCaml. So it's pure. So you don't have mutation in that subset. So you have to know your purely functional programming here. And last is Reason LIGO. The last added was Reason LIGO. This is inspired by ReasonML, which is itself a syntax inspired by JavaScript, which is put on top of OCaml. It has quite a large community, perhaps as large as the OCaml community, so it's widely known. For those people, we have that as well. And to show you how rich this is, even within Pascal LIGO, there are two flavors. Of course, this makes it very important for us to offer pretty printing facilities. And even we plan to do a transpilation between syntaxes. So if you have a smart contract on Pascal LIGO, say, you may want to have the same contract on Camel LIGO or vice versa. And this being done automatically for you. One of the reasons is because you always want your smart contracts to be as widely reviewed as possible. Remember, they are publicly available anyway. On the chain, especially if you put them in a comment in the Michelson, which is possible in theory. And anyway, you would want them to be reviewed before you deploy them on chain. So for that, you don't want to perhaps be stuck in one syntax. If your programmer is not familiar with one, you can choose any other automatically. So I will be introducing very, very, very quickly, because we have very little time, the non-Tezos specific features. I picked some specific features that are non-Tezos specific. Rémi will talk about something, will explain some contract, right? So more practical later. Well, okay, so some interesting things. So when you call functions in LIGO, arguments are copied, but also the environment. And inside the function, if you reassign variables that in an outer scope, the effect is lost when the function is finished. So it allows you some form of imperative programming, but limited, in a limited way. So from the outside, functions look as if they are pure. Of course, if you don't query the chain, all right? Because this is impure. This is specific to the way we program. We have higher order functions. I know this has become popular thanks to functional programming in the last 10 to 15 years. So we have lambdas, anonymous functions, and we can pass functions to functions and things like that. Even in Pascal LIGO. Anyway, the original Pascal had already that from Algol. So there you go. Something we don't have is user-defined recursive data types, simply because we still don't have recursive functions. So we do have, what we did was to lift Michelson types, which are some of them recursive, like sets, at least lists you may aware of, and maps, lifted as predefined types in LIGO. In the future, we plan to have very soon, I think, a limited form of recursion available for functions. So this is very general, but yeah. So let me show you. So we have variant types which are coming from the, again functional programming world. So here you define a coin as being head or tail, and what can you do? This definition these definitions are equivalent to enumerated types you find in many mainstream languages. You can go a bit beyond and associate some data to each case. So you can actually have data that is defined by case, which is very useful for many applications. So if you want to flip a coin, this is how you would write it in Pascal LIGO. So you see you have lots of keywords. The feedback we have currently is that some people like it very much to have lots of keywords because they help them to keep in mind what they're doing. So I don't know, this is up to you. In Camel LIGO, so this looks exactly like in OCaml. This is correct OCaml and correct ReasonML code actually. And just the last feature I would like to show you before Remy goes and tells you more about one specific contract we have. So you get an idea of a specific application. Would be looping and how we do loops. So this is I picked this very simple and I hope widely known algorithm to compute the greatest common divisor of two natural numbers, and this is how it looks like in Pascal LIGO. So you see it's quite, I think, readable. You can see you have your while loop, and you can reassign to variables multiple times, okay, after declaration. So we hope that this will be quite easy to grasp for someone who is used to an imperative language. Okay, so Camel LIGO is really like OCaml, so we don't have loops. By loop, I really mean a syntactic construct like this one, like while, okay, where you have a piece of code that is repeatedly executed until a condition is met, okay? Since we are in Camel LIGO dealing with a purely functional language, we don't have that because we don't have mutation. So if the condition is true, it will remain true forever. So loops would always either never be executed or always be executed, which is useless. So what do? We have a predefined functional iterator, of course. So this is the same program written in Camel LIGO. So you can see that we have a loop fold while, which is predefined, and it applies repeatedly the function iter until a condition is met. And how do we know the condition is met? Is because iter returns a pair. And the first component of that pair is actually a Boolean that tells you whether you have to stop or not. Perhaps it's clearer if we use a predefined function stop and resume like that. So this is what we recommend until now. Soon we will going to improve on this, but as you can see, this is pretty short, and I think it's neat. All right, just to mention something about the backend of the compiler, we do have lots of optimizations. So the Michelson we produce is not ridiculous. Some cases we are doing changes to the way things are represented internally. So temporarily we may have some, too big a Michelson produced, but we work always on that. And for example, we have inlining. Okay, so you can suggest or tell the compiler to inline your function and some constants. The compiler is doing that, but you can also enforce it. So it looks it feels like a real programming language. It's not a toy language. Just a word on what we are going to do and we are planning to do. We are working on a new type system, much more powerful. Currently, we have you need to annotate a lot with types as well. Adrian mentioned formal methods earlier. We already have been working on a certified backend in Coq, which means that at one point we will be able to extract in OCaml, because the compiler is written in OCaml. We will be able to extract the backend from logical specification of what is a correct compilation. Okay, so this needs to be specified, and it's not completely clear now, by the way. But we have been working on this for a few months now, and so yeah, so here we are. I think it's time for Rémi to say a few words. I had this intended, but I think he will show you on the code itself. Thank you.
Sorry, 1 minute. Sorry, so I got to set up my computer, so just a moment. Yeah, that's great. So I cannot actually see what I cannot see the code actually. There is a screen in front of me and the font is really small. So I'm going to do a bit more settings. This is going to work. Right? Can you see? Can you see everything? Yes. Yeah. Oh yes, yes. I will put a light team. Good idea. Okay. There you go. Okay. So, the idea here is to present a small contract, a crowdfunding contract, and to go through, if I have time, to go through an actual execution of it. Not on-chain, but with our dry run command. So, first thing you want to do when writing a contract, I believe, is to define some types. So, as you may know, a contract is taking a storage type that you can define, a parameter type that you can define, and the contract itself is a function that takes a parameter and a storage and returns a list of operation and the new storage. So the storage you get in the input is the initial storage stored on chain, and the one you compute is the new storage. So for our crowdfunding, we have a parameter which is a variant type, and so the constructors here are just well, the action we would like to perform. So there is just back, claim, and redraw. And what do we store in this contract? So we store the owner of the contract, which is an address. I mean, sorry, the storage is a record. And yeah, so in this record we have multiple fields, and one of them is the owner. The target is how much we would like to get in this crowdfunding project. The deadline is when the project is over. I mean, the gathering of the fund. The backers, are those who gave money, and this funded field is basically, I'm telling you if the project has been funded or not. Okay, so here I have. Can you see? Okay. So here you have some utility functions. I will go back to them later and show you actually the main function of the contract so that it's clearer for you. Okay, it's here. So this function is taking an action of type parameter, so it's either back, claim, or withdraw, a storage, which is the initial storage, and return, the type return, which is here, the list of operation, and a new storage. So what this main function does is it's matching on action. so the parameter, and dispatching to the few function I will show you above. So for back, for example, if you want to back the project, what we first do here is that we check that the deadline is not passed. If it's passed, then we throw an exception. I mean, you can see it as an exception. This basically tells you that the execution of the contract on chain will be aborted, and that nothing will be changed. So if the deadline is passed, we throw this exception, otherwise we skip. And then we are matching on the sender. I mean, we are trying to get the sender entry in the baker's map here that I defined, sorry. So the backers were a map of address to Tez. So we are trying to find the sender entry, and if the sender doesn't exist, then we create an entry for it. Otherwise, if you already donated, then it will just be skipped in this contract. Not sure if it's very good, but at least in this example, sorry, it's like that. So now, sorry, let me move this bar here. Okay, so claim. Same thing. We are going to do a few checks. So if the deadline is passed, or rather, yeah, if the deadline is not passed, then we fail. Yes, so here we check if the contract, I mean the crowdfunding, has already been terminated. If it has, then you cannot claim your money back. And here we check if you are a backer, because if you are not a backer, you cannot get your money back. So same thing. You have this if, then fail, which is kind of an exception, and then skip if the condition was not true. Here, what do? We get the baker balance with this utility function, so we'll show you in a moment. So get baker balance is here. We need a lot of type annotation, as Christian has said, because the new type system is not here yet. So that's why you have to annotate here. You see an annotation. So this function is taking an address map, which is holding the binding between the address and the balance, and returns a balance. So you match, again, case. Find opt will return an optional value. So it's a variant type, an option. Basically, some or none. So if it finds something, then it will return the binding of the address in this map. So in this case, T. If it's not, it will fail. Couldn't get the backer balance. So again, we were here. So this is giving you the balance of the backer. This test, Tezos get contract, is basically checking here, in this case, that the sender, I mean the sender, sorry, has wait, what do we do here? No, it's just getting the contract basically to be able to create a transaction just after. So it's taking the sender, and it's going to we are going to create a transaction of this given balance back to the sender. Why do we assume that sender is a contract? I'm not sure I got the question, sorry. Okay. So I told you before that the contract is returning a list of operation, and this list of the operation is actually what will change the chain states. Where? Sorry. This one? Yeah. It's the. Because this function is actually expecting the contract, and this is checking the type of the parameter of the contract. So this actually type check the contract, saying the parameter of this contract sender is of type unit, or is an implicit contract, but I'm not sure you have. I mean, you went.
Yes, you can. You can transfer to contract with unit type. Just transfer to user.
Yep.
If you transfer to simple address, you can cast it to contract type, but you just send message unit, which just, if you familiar with C, is just void.
All right, thanks. So yes, I was here. So yeah, you build this operation, which will be the transfer, and then you remove the sender from the list of the bakers, and you return the operation and the new storage, which is basically the same, but with this baker removed from the list. And the third action you can perform is redraw. So when the deadline is reached and the target is reached, then you can, the owner of the crowdfunding contract can redraw the money. So what we do is that we check if the sender is the owner. In this case, we check if it's different. So if it's different, of course we fail, because only the owner can withdraw. Same thing here, deadline, it has to be after the deadline, and also the target must be reached. And then we are doing the same thing, so we are typecasting, again, the sender against the unit. And we are building the transaction back to the owner of the contract. And we are changing this funded field to true. And same thing, we are returning this operation and along with the new storage. Do I have time? 5 minutes, okay. So I'm going to show you a few execution. So I wrote a small script that has some commands. So LIGO, as a command line interface, has multiple commands. So you have compile contract, dry run, interpret, and others. So you can check it out. So the first thing I would show you, if I can get my terminal, yeah, here. Okay, is the Michelson code that is generated if I compile this contract. So it's yeah. So I don't know if you have any experiences, Michelson, but this is how it is. This is a Michelson contract. So I'm not going to explain everything here, of course, but this is how it looks. Okay, and now I'm going to explain how to dry run a contract. This is here. So we call dry run on a given source file, of course. We give the source file here, and then the main function name. So here it was main, right? And we are giving a parameter. So we want to execute the contract here. So we are giving back, for example, and giving an initial storage. So I put some initial test initial storage, let's say here, and I'm using it in the script. So it's called test back here and test back here. Okay. And then you can give some chain context, I would say, in order to do testing. So here you have the predecessor timestamp command, which is basically allowing you to set the time of the... Okay, I have to conclude, sorry, but no time for that. So, yeah, thank you. Yeah, well, you want to... Well, maybe I can execute the contract, actually. I don't want to be the one that is late. So, yeah. I will execute this, and you will see what happens. Sorry. Okay. Execute again. Okay, so here I first interpret the test back. So I have my initial storage. So this is a representation of what you wrote in LIGO, but it's not actually LIGO code because we don't have the syntax pre-printing yet. So yeah, you can see here that you have a map with multiple baker. The contract is not funded, and the owner is this guy, and the target is whatever. 100 million meters, something. And I ran this contract and I got fail with deadline pass because I called it with the timestamp that is after the one that is defined in the initial storage, which is here and which is not very well pre-printed, sorry. But yeah, so this was my first test, and this is how you can write some test in LIGO. Yeah, thank you.
Okay, so thank you, Rémi, thank you, Christian. So we'll take a few questions. Yes.
I'd just like to know if you have a unit testing framework with LIGO.
Okay, so this is a good question. So if you want to unit test a contract, the best way to do it, I would say, is to use another. I showed dry run, which is running a contract and checking that what you run is a contract and has everything that is needed. But there is another command line, which is run function, and you can run an arbitrary function. So I would recommend to, if you can, write your test function and execute it using run function. That's how I would do it. But you can also use dry run and parse the output of dry run. People are actually doing this, but yes, there is some work to do in order to have proper unit testing for contracts.
So follow-up question about testing. So, so with LIGO, you have some virtual machine, yes, right, or some interpreter, which will execute the code with a storage, and you can interact with it without the blockchain, correct?
Again?
Based on what you saw, how do you run it?
Okay, sorry. So dry run, the contract is compiled to Mikkelsen, and then dry run is calling the Mikkelsen interpreter directly to get the results, and the results are...
So how do you do, like, if you want to have a sequence of some commands to run? And how do you test it?
Storage from previous to next.
So the storage is kept, right?
You have storage state 1. You have executed function. You have storage 2. Pass storage 2 to second.
Okay, so I need to copy this storage, like the output of the of the run. Okay, so not very friendly.
So if you want to test your contracts, you may use Takita. It is a JS library, and you may write your test normally and check state changes.
Maybe it's more general about Tezos in general, but I see that you output this wall storage at each time. But if you have like a lot of baker, I imagine that there is a kind of compression or optimization so that you don't store on chain the whole map each time.
Oh yes, there is another. I mean, there is the map type and there is the big map type, which is actually stored as plain in the chain, but the access at least are deferred. I mean, the Michelson interpreter will just compute a diff with the old map and apply it.
Okay, but only the map is treated like that. The other storage types are just always written into the blockchain.
Yes, I believe. Yes.
Okay.
So, thank you. I'm sorry we have to move on because we are late already a little bit. Let me add to the previous talk that they have a website, ligolang.org, I guess. There is a Slack channel, and so it's on the Slack, Tezos Dev Slack. Christian? Slack channel? Okay.
Yes, it's the same as the Magic Labs.
Yeah, so you can get information from there, especially people listening to us remotely. Also, we'll have a break in 15 minutes, and that will be a great opportunity for the developers to discuss with the LIGO people. So thanks again, everyone.